Now, without any further ado, let's go ahead and actually get into talking a little bit about .NET and doing some performance optimization. So, to kind of introduce you to a little bit of theory here, and I'll drop a link to this in chat. This is from Adam Sitnick's website. Adam is one of the developers at Microsoft who works on benchmark.net and does all sorts of high performance stuff in .NET. So, a little bit of detail about him. So, long story short, in terms of the magic behind spans here, this is normally when you're looking at a garbage collected programming language like .NET, you typically want to look at, if you're concerned about performance, you want to look at the generation of garbage collection performance that's in here. So objects that are declared inside, well, basically really garbage collected inside generation 0 tend to be very short-lived objects. To give you an example from Akka.NET, if I take a look at, this is some code I was working on last night. Let me close all those tabs. And let me go ahead and switch. Let's see. I need to grab a new console here. This is my Kubernetes stuff that I was working on earlier today. Let me go ahead. Repositories. All right. And let me switch back to the development branch. Bring that down. Merged in some changes earlier today, so I need to make sure I have the latest set with me. All right. I should have all that available now. If I go and take a look at, let's take a look at a piece of what's called the hot path. This is parts of our code that gets called pretty frequently. If I take a look at our, let's say, actor path down here, this is the data structure that describes the address of an actor in Akka.NET. If I go down to our, oh, here's a good example. Well, actually, no, not a good example. Let me go a little bit further. Let's see. Actor path.parse. All right, here we go. This is one of the methods I was working on. So a good example of, let's say, Gen 1 garbage collection is if I step into this method, I'm going to go ahead and create right here. I'm going to go ahead and create when I call absolute path.split. I'm going to create a little array. So that array is going to be allocated right here. And then I'm going to go ahead and iterate over the elements of that array here. In fact, I'm going to go ahead and skip the first element because it has nothing useful in it. And I'm going to go ahead and concatenate this and turn it into a little tree of these actor path objects here. Well, this first element in this array is going to be part of Gen 0 garbage collection because it's only going to be used inside this narrow scope. And so the garbage collector will go ahead and mark that object right here. And then by the time this bracket exits, the garbage collector will mark it for deletion. And those objects tend to get essentially collected and scooped up pretty much right away. So that's Gen 0 garbage collection. Gen 1 would be more like, so Gen 1 is actually the hardest for me to define out of all of them. Gen 1 of the garbage collection heap would be like the output of this little actor path try parse right here. Let's say this value gets copied up into a, let's say, a remote actor reference, which is a temporary single use, well, not single use, but it's a sort of a temporary pointer to an actor in another process. Well, once that remote actor ref goes out of scope, and it might go out of scope in the course of processing a single message, all those objects that are inside of it will be marked for generation 1. So generation kind of determines how old this object has been. And the older the generation an object is, the more roots it tends to have, meaning the more objects it has references to. So the garbage collector can't really get rid of it until it knows that object's been fully dereferenced by all of the other objects that aren't being actively used, or that are being actively used too. Gen 2 is where the bulk of your objects are going to live. These are longer lived objects. And from a performance point of view, Gen 2 is usually where the focus is. Ideally, we want to go ahead and try to avoid having objects getting collected in generation number 2. This is the most expensive type of garbage collection. In older versions of the CLR, this used to result in what's called a garbage collection pause inside our system, and that can really damage throughput quite heavily. So the rule of thumb kind of was, either make sure nothing gets into Gen 2, and I say rule of thumb, people tried to follow this, but it was more aspirational. Very few programs could literally do this. But it was either keep objects in Gen 2 forever, meaning they never get collected until the process shuts down, or never let them get into Generation 2. That would be the ideal in one of these scenarios. Now, the other part of the heap, in terms of allocating memory, is this little bit over here. LOH stands for the large object heap. The large object heap was for objects that basically exceeded some base threshold size. I don't remember off the top of my head what those values are anymore. I think it varies a little bit based on the version of the operating system you're on, the generation of .NET you're in, etc. But these would include things like, let's say, if you were caching fairly large binary objects like images or other results like that, those would be the things that could potentially live inside the large object heap. And so one of the problems that old versions of the .NET framework used to have is that objects going into the large object heap could never be collected again. That's one of the reasons why we had things like app pool recycling and IIS back in the day. Modern versions of the CLR don't have this problem anymore. But one of the problems that Adam kind of points out on here is that large object heaps tend to lend themselves to memory fragmentation. So your operating system allocates this contiguous block of memory for you to use in your application. And let's say you don't use all of it right away. Some of it goes into the large object heap. Some of it goes into the other areas of the generational garbage collector. But eventually, as your application's usage patterns change, some objects that aren't frequently accessed might be moved into the page file. And then they might be moved back out of the page file when you need them again. Page file is basically virtual memory. It's an area of disk on your computer that the computer parks objects that aren't needed in memory right now. That way, a computer that has 12 gigs of memory can actually do 30 gigs of work. And the difference is, the memory that's not being used right now sits on the page file. Page file hits are a really bad thing for production, high throughput applications because it involves disk I/O, which is expensive. But the other reason why the page file and the large object heap can create some problems is for really large objects. After a while, you can end up fragmenting memory, where some of the object can live in this sector over here, some lives in this other sector over here, and that's going to slow down your ability to go ahead and access that object all at once. It's a lot easier when you have contiguous blocks of memory to do it. So kind of like how you have defragmentation for your hard drive, parts of the garbage collection system inside .NET are going to go ahead and try to compact memory periodically. Now, there's some other techniques other than memory compaction for trying to preserve performance, but that's one that's been tried for a long time. All right, so let's go ahead and skip past some of this stuff. This is kind of details on how some of the garbage collection bits work. All right. Yeah, this is also a good point that Adam brings up here. What he's talking about is that in a server environment, garbage collection works fundamentally differently. In a normal, let's say, consumer process, like the type of thing you'd launch on your own Windows PC, you can basically get one big heap, right? Well, in a server-side environment, in order to maintain maximum throughput, in order to avoid, in particular, garbage collection pauses when you're working on Gen 2 or on the large object heap, we actually go ahead and parallelize the heap. And make sure, in this case, looks like in his diagram, every single core gets its own unique heap, which sounds right to me. So that way, if we have to go ahead and do a GC pause, it's only affecting 1 out of n cores at any particular time. So this is like asynchronous garbage collection behind the scenes. Now, I'm kind of building up to my point here. I'll skip past some of this stuff, which is in most major, let's say, programming language runtimes, you have the heap, which is where your big long-term memory objects go. And in managed languages like C# and Java, you have this problem of garbage collection you have to deal with. Well, one of the other data types we have access to is what's called a stack allocated data type. So the stack is basically allocated memory on demand, usually for very simple data types that can fit into basically a sort of a stack-aligned piece of memory. And so these tend to be primitives like integers, they can be arrays of bytes, that type of thing. And so stack objects are allocated on demand, and typically when you're passing, let's say, values that are on the stack between functions, what's normally happening, if you've ever done any C++ before, you probably remember having to do passing by reference or passing by value. Well, by default in the CLR, these stack types are passed around by values. If I go ahead and create an integer up here and I pass it into this function, I'm actually copying that value. And that's because the stack is very inexpensive to work with. Everything gets automatically freed on the stack once a value goes out of scope. So stack allocated objects are very inexpensive compared to their heap data types potentially. So like Adam points out here, it was really only value types that could live on the stack before. So these were mostly simple data structures like integers, but they also could include some more complex data structures like time spans, for instance, or custom data types as well. Well, get past this. Great, fine. All right, here we go. This is what I want to get to, the meat of the matter. The span data type. So one of the things that the span changed is that normally it was only value data types that could live on the stack. Well, the span is what's called a ref struct, meaning it is actually a reference type that can live on the stack. And this kind of opens up a whole bunch of potential for doing all sorts of zero allocation programming structures. Now, I'm not going to pretend I understand all of them. I'm still in the process of learning this myself, and we're going to go ahead and delve into some of that tonight. But largely what spans provide are basically a uniform API for being able to work with arrays, work with strings and substrings, and memory buffers. Byte arrays in particular is what we're talking about here. So has very low overhead. Stack allocated types tend to be that way. And it's read-only. So any data that gets copied into a span is typically going to be immutable, but it can be read, it can be passed around, etc. And in older versions of the .NET runtime, let's say .NET 4.5 or maybe .NET 4.61. To get access to span, you have to go ahead and pull in the system.memory NuGet package. That'll go ahead and introduce all these primitives there. We're going to be working in .NET Standard 2.0 tonight, which already has built-in support for this. So we don't actually need to reference any additional packages. But okay, you got to upgrade to language version 7.2 C#. So I think the current version of C# that is out right now is, I believe it's C# 9.0. Maybe there's a 9.1. Build just happened today, and I know they're already talking about C# 10 on the horizon, but 7.2 is the version that you need to really work with stacks, because that imports the ref struct feature here. Now, he's offering some examples here using a couple of more sophisticated features of .NET memory management, such as doing, basically generating this is essentially generating a pointer expressed as an integer to a 256 byte block of memory here. This is basically how you work with unmanaged memory. So if you've ever done any work with, let's say, like COM components or a native interop in .NET, this probably looks pretty familiar to you. Most of what we're going to be dealing with tonight is all managed memory stuff. So here's some of the APIs in Span, and then you might actually have the ability to go ahead and modify some of the contents here, because we also have, here we go. So you can go ahead and make sure that the memory is read-only. You actually can't modify anything that's stored at this location here on a read-only span. So that's one thing that is a little different, is that a normal span can be mutable, a read-only span is not. There's also another type that we're not going to spend much time talking about tonight called memory, which goes along with this. Memory is another way of being able to go ahead and wrap data that can't follow stack semantics. And one of the things we'll talk about a little bit is essentially how you can go ahead and return and pass spans around inside your application. Now, that's sort of my prelude to talking a bit about spans and doing a bit of C# performance work. So let's go ahead and actually let me go and grab my branch that we were working on before. Perf actor path parse. Let's grab this. Okay. Grab that. Okay. And I might need to go ahead and pull some changes there. Perfect. All right. So let's take a look at some actual Spanification code. So the same method we were just looking at, lo and behold, I have done a little bit of legwork already inside this code. So This is definitely in the hot path of Akka.net execution pipeline. This little bit of span code here. And by the way, one nasty little constraint that we have to work with in Akka.net. In fact, let me go and pull this up. Another tab here. One nasty constraint we have to work with for doing some performance optimization in Akka.net is if I scroll down, we are targeting .NET Standard 2.0, which means that users who are using .NET 4.61 and later can all use this. So some of the nice new APIs that are available using spans, I actually don't have access to because those are only available in .NET Core 3.0 and up. So that's one limitation we're going to have to work around. So anyone dealing with, let's say, a legacy application is going to run into this. So here I have my try parse method. This gets called every time a message gets deserialized over Akka.remote. So that's something that we have to kind of worry about a little bit. So one of the first things you can do is that you get an extension method once you have access to the span APIs, where I can take the string and call as span. This will go ahead and give me access to the underlying character buffer that the string contains, and I can do certain types of manipulation on it without having to perform a full deep copy of the string in the first place. So what I'm going to do is take that string.split operation, and I'm going to try to avoid allocating strings for it. Unfortunately, I end up failing in doing this. So I spent quite a bit of time working on this already. It took me a little while to handle all the edge cases that our old code did, but it does work. So here's some of the things that we have going on here. I take my span, and I'm going to do a little while loop. I'm going to say, okay, I'm going to go ahead and look for an index of, let's say, the slash character. I'm basically re-implementing string.split. And I'm going to say, all right, if I have a slash that's at a position greater than 0, I want to go ahead and basically slice. So basically this allows me to kind of move the buffer forward. And I'm actually going to create a new read-only span when I do this. I'm going to say starting from the start of this span, I want to take all the way up until we find that slash. And then I want to go ahead and copy that into a brand new string. So I'm still allocating new objects here. In .NET, I believe it's .NET 5, there's actually a method called string.create that'll allow me to go ahead and pass that span in directly. And I can go ahead and create a new string without actually having to copy the memory. I would very much like to have access to that, but I don't at the moment. So I also tried playing around with, by the way, in case someone mentions it in chat, I tried playing around with passing, you can use a little bit of unsafe code. In fact, let me grab an example of that. You can actually go ahead and copy character pointers using unsafe code in .NET. And that's what a lot of people, including myself, used to do to go ahead and try to avoid copying strings and duplicating them all over the place. But that actually still results in having to go and allocate a brand new string in a lot of cases. So our Akka.remote library uses a least recently used cache, and that's what this is right here. So this is actually how we go ahead and compute which part of the hash bucket this value is going to go into. And so this needs to be really fast because we're computing this thousands of times per second, maybe up to hundreds of thousands of times per second potentially. So this is using a type of, I'm trying to remember, I think fast hash is actually the name of the algorithm. It's been like 4 years since I implemented this. What we're going to do is we're going to go ahead and create an unsafe block right here. You have to go ahead and compile your application with a special flag to let it know you're doing this. And then I'm going to go ahead and basically get a fixed pointer address to the first character in the string right here. And based on the string's length, I can actually use a for loop to iterate through all the string characters without having to make a copy. Otherwise, the previously type-safe way of doing this, which I don't think we actually use this code anywhere. Yeah, just in benchmarks and in a unit test. We had to go ahead and call it to character array. And this actually would go and create a deep copy. Well, now I could change this to as span. In fact, you know what? Let me go ahead, just to illustrate the performance difference here. Let me go ahead and grab our Akka.NET project, and I'll go to benchmark, Akka.benchmarks. we'll go ahead and run our benchmarks here so I can show you the before and after. So let's give this a shot. And this won't take too long. This is actually a pretty fast executing benchmark in the grand scheme of things. All right. Man, that rye whiskey's good. We have a lot of compilation warnings. I should probably set aside some time to go ahead and deal with that. All right, 14 fast hash benchmarks. Let's run that. All right. I'm liking the music right now. This is melodic. All right. You're liking it too, him, Jay? All right, well, that's good. I'm listening to a lot of ambient sort of music lately just to help keep me focused while I'm doing my work. All right, here we go. This one's going a lot faster. I guarantee you this is the this is the unsafe implementation of that hashing function we're seeing run right now. So let's see. All right, in fact, you know what? I'm going to go ahead, add a stream marker. We're going to do fast hash before and after. All right, there we go. Add a little stream marker. All right. So our performance. Oh, hey, H3. How's it going, man? You're a rye guy at heart. I like all sorts of things. Good malt, rye, anything, you name it. So let's see. This is my unsafe implementation. Takes 6.4 nanoseconds to run. Allocates no memory. My fast hash of string allocates 40 bytes. It's probably the length of one of those strings that we're copying. And takes 4 times as long. So that's the impact of having that much Gen 0 garbage collection right there. Now, one thing I can do to go and improve the performance right away is change that to as span. Clean that up. All right. Now, if I go and rerun this, so let me go ahead and just save. Let's see. Grab that data. Let's see if I can go ahead and open up a notepad here. Yeah. All right, this is our before. Let's go ahead and compute an after. Okay. Fast hash benchmark. Let's do that again. All right, now this is operating in about the 8 or 9 nanosecond ballpark instead of the 24 it was in before. So my guess is we've effectively eliminated any garbage collection that was happening. So let's go ahead and see what the final values are. All right. Okay, and here we are. No allocations at all. And we have 8.81 nanoseconds versus 6.360. So the difference between these two is basically doing unsafe pointer arithmetic versus doing totally type-safe spanification. So pretty amazing difference in performance there, and we're able to go ahead and keep type safety. So there you have it. That's another example. That's sort of a really simple example of being able to go ahead and use spans to improve performance to some extent here. So I'm actually going to go ahead and commit that. Let's see. Go ahead and commit that. Type safe fast hash. All right. Go ahead and save that value. Oops. Entered my GPG key in wrong. That's happening off screen. All right, there we go. Got that done. That's one example of spanification there. Now, some of the other ones, if I go and take a look at our little pull request, in fact, I'll go ahead and push my most recent values up to here. These were our initial sort of actor path benchmarks that we were working on. So we were allocating, on average, every time we had to go ahead and parse a brand new actor path. This is like over a kilobit of memory here. That's quite a bit. It's because those actor paths can be large, but most of the memory is actually being allocated by a method we can't control. Most of it is coming from this try parse address method, which if I step into, is using URI.tryCreate underneath. So this method, which does all sorts of different little parsing to try to extract the various URI parts and everything else, this method's very expensive. It does a lot of, how should I put this? It does a lot of specialized parsing that kind of follows different W3C schemas and that type of stuff. I personally don't feel like reinventing the wheel on that. I think even though I might be able to come up with a narrower use case that is very performant, there's still quite a bit of risk exposure in doing some of this stuff. Although, you know what? Actually, maybe that's not the end of the world. Okay, you know what? I'm actually going to give that a try. I feel up to it. Why not? So what parts do I need to go ahead and parse? What parts do I need to go ahead and create an address? Protocol, system name, host, and port. Okay. So I get from the URI, I get the actor system name from the URI.userinfo. I get the host from there and the port. And the protocol, where do I get the protocol from? The scheme on the URI object. Okay, well, this might be worth exploring, so we will certainly take a look at that. But the other things we've done in terms of working on the address parsing, we were able to go ahead. We were actually able to go ahead and reduce. This is not the right area. Here we go. We were definitely able to go ahead and reduce some of the allocations that occurred in here. So after my first set of changes, so this took, by the way, nearly, this is, let's see, 2,000 nanoseconds. That'd be 2 microseconds, roughly, I believe, to go ahead and run that routine once. Well, I got very excited about this because I thought I was a mega genius and made a whole bunch of gains, but it turns out I actually broke all the parsing code, and we had about 90 unit tests fail after that. And the reason why it was only 90 is because the unit test, the test suite short circuits once it finds some failing tests and decides not to continue after that. So that was not fantastic. So after a bunch of trial and error, I was finally able to go ahead and get back to here, which is allocating, I think, 992 bytes. We're under a kilobit now, at least. And we were able to shave off about 300 nanoseconds. So that's an improvement. And then I had to fix bugs again. I think we lost a few nanoseconds. I had to go ahead and do some more stuff. But this time we had a working solution that definitely worked. And then one of the little dependencies we had internally, let me go ahead and find that. Let's see. Well, this is something else I came up with, my span hacks class. So I was able to go ahead and replace the int32.parse method to one that used a span. Now, in .NET Core, I think maybe it's .NET 5, maybe it's .NET Core 3, I don't remember. One of those platforms actually has a method that does this, but because we're running on an ancient platform by comparison, I had to go ahead and write what we call a polyfill, which basically means that I had to go ahead and backport that method. And by the way, in case you've never done, let's say, low-level C++ or anything like that, this is how you convert a string to an integer. Oh, in fact, that reminds me. I actually need to go ahead and move that and turn that into its own static method. That was a piece of feedback I got on Twitter today, so I'm going to go ahead and incorporate that, rather than making it a local function. So the way you actually go ahead and convert, using a span in this case, the way you actually go ahead and convert an integer to a string, a string into an integer, check the first character for a sign, you advance the iterator, then you go ahead and look through each one of your characters. So long as it's numeric, you keep going. And then because you're actually working on setting each significant digit, you go ahead and take the value you have right now, and you say that value is equal to that value times 10. That basically goes and moves the next slot to the next significant digit. And then you add basically the Unicode numeric value expressed as a byte of that character minus the Unicode numeric value is 0. And the delta between those two byte code values actually gets you an integer between 0 and 9, because all those characters are allocated sequentially to each other. So this is basically how you can go ahead and write your own, I guess in C++ it's called stir to I, or S to I is what it's called, but in .NET it would be int32.parse. So anyway, I had to backport this little bit of functionality to help cut down on the number of strings we needed to allocate for doing parsing. That was not something I would recommend doing, but because, you know, we're trying to go ahead and make this as performant as possible, I thought, why not? And then we're also able to, if I take a look in here, we overloaded the slash operator. And one of the operations we have to execute is this actor cell.get name and UID. Well, before, if I go to implementation, we actually called this split name and UID, and this returns a class. So this actually created some additional Gen 0 garbage collection pressure here that we wanted to try to avoid. Well, actually, it might have even been Gen 1. Let me take a look. Let's see. Our before value, so it wasn't definitely not Gen 1, but Gen 0. We had 0.2365, and then we had 0.2136 after we got rid of that type. We went ahead and we turned that name and UID type into a value tuple down here. It's the same piece of information, just that this piece of code is like 7 years old. So, you know, and I don't know why I didn't make it a struct back then. Probably because this type of performance stuff wasn't as important when we were first getting the framework up and running. So we went ahead and marked this as obsolete. We'll delete it in the next minor version of Aku.NET.